Thomas Kutti Matthew. Participants, please mute your audio to avoid any disturbance during the program. And you can type in your queries, doubts in the chat box. During the Q&A at the end of the session, it will be discussed. Today, we have with us Professor Binu Paul to chair this session. Professor Binu Paul from the School of Engineering, CUSAT, is an experienced teacher and researcher in the area of antennas and microwave, with several publications in the same domain. We welcome you, sir. Over to you, sir.
Binu Paul, ma'am.
Good evening. I hope I'm audible.
Yes, ma'am.
Yeah. Good evening, dear participants and the resource persons of the day. In fact, we have 2 resource persons in the pipeline. And as we all know, this workshop has been going through a beautiful blend of academical, technical, and industry-oriented sessions with hands-on sessions. And today we have somebody from a different domain, from the defense section. And I consider it as my pleasure to introduce Lieutenant Colonel R.K. Mishra. Sir has retired from the Indian Army services to pursue his academic interest, I understand. And he's a EMI, EMC consultant and a facility manager, a military EMC evaluation specialist, and communication system maintenance expert. He's as I told you, he's a retired Indian Army veteran, having served in our services for around 22 years. And he has commissioned several EMI, EMC deployments, and has worked on the electronic warfare systems, I understand, and also in the EMI, EMC setup of Indian Army. He has a vast experience in maintenance of Indian Army equipments, weapon systems, and also does consultancy work of EMI, EMC trials of Indian Armed Forces, and also in the procurement of Indian Defense Forces. And that itself is a huge responsibility, I suppose. And he's an expert in handling the EMI, EMC response of the anechoic chamber. And the title of the talk itself is quite attractive. So I welcome you all to this talk, and I welcome our Sir R.K. Mishra, Sir, to this talk on the relevance of EMI and EMC in armed forces and industry, anechoic chamber, Indian Defense Procurement Clause, requirement for EMC, EMI, and the EMI, EMC trials by Indian Army. Over to you, sir. A warm welcome.
Thank you, ma'am, for the kind words. Without wasting any time, I'll just get to the my presentation.
Sir, I suppose you have to adjust your camera a little bit so that we can see your face.
Yeah, ma'am. Just a second. I'll just. I think I have not shared computer already. Okay. Yeah. So this was important. Yeah. So am I visible now?
Yes, very much. Thank you.
Thank you, ma'am. So my slides are visible, ma'am?
Yes, sir.
Okay, thank you, ma'am.
Yeah.
Yeah, so I welcome all for this session of Hello EMI and EMC. As ma'am has already mentioned about me, I have served for around 22 years in the Army, and I have worked on basically electronic communication systems, EW systems. I have managed EMI, EMC facility of Indian Army. And currently I'm pursuing my PhD also, as I had interest for academic interest, and also do consultancy work on EMI, EMC, maintainability, and defense procurement. Defense procurement in the sense I don't do any work for Government of India or any of its like autonomous bodies, say Army, Navy, or Air Force, but definitely any industry, any vendor who wants this kind of consultancy or advice on these things, that I render. So this is the overview. I'll be covering my presentation under these headings. So I have gone through the schedule, and I've seen that a lot of technology and details and all those things have already been mentioned and thrown and told by various eminent speakers. So I'll not be concentrating on those. I'll be digressing from them and will be mostly touching from the practical aspects of it. So these are the references. In the audience, I am actually not pretty sure about the audience, but I am assuming, like while I was preparing this presentation, that there would be a good amount of good numbers of students and some people from the industry who would be wanting to know about how EMI, EMC is there for when they have to field their equipment for procurement in the army or say the defense forces. So these books are very important. This so this book, Henry Ott and Clayton, these two books are like I would say Bibles. One EMI EMC engineer must have the copy of this and should always be keeping them with them. This book is also very good. This is about anechoic chambers. So if you are like into designing anechoic chambers or like that, so you can refer this book. These are some other references. The last one is important because he was the speaker on like 30th July, DRDO RCI scientist, and I have used one slide of his in my presentation. So I will be showing you one YouTube video, and with this you will come to know about the introduction of EMI EMC. Now in this, air hostess is like before taking off the aircraft, she briefs the passengers, and I'm pretty sure even a seasoned professional would find it very difficult to answer whatever like the questions are being asked.
Ladies and gentlemen, as we prepare for takeoff, please turn off all electronic devices.
Why?
What's that?
Well, why do we have to turn off our electronic devices?
Because they can interfere with the plane's navigation.
Oh, okay.
So anyway...
How?
What's that?
How do they interfere with the plane's navigation?
Oh, because the electronic signals can interfere with the signals between the plane and the radio tower on takeoff and landing.
Oh, okay. Gotcha. That makes sense. Thank you.
Okay. Let's all make sure that our seats are fully upright.
Wait. I mean, I get why I can't have a radio or whatever, but how's my Kindle going to screw things up?
That's a good question.
It's not just about radios. All devices have an electromagnetic field that can interfere with the radio frequencies.
Okay, that's cool.
All right, please make sure that all tray tables are...
Wait, so you're saying that a $90 million aircraft can't ignore the signal from my $40 iPod Shuffle? That's weird.
She's right. That is weird.
Yeah, now I'm confused again.
If they're so dangerous, why do you allow devices on the plane and not, I don't know, gels?
Yeah, could I hold this plane hostage with my 3DS?
Some devices are more dangerous than others, but there isn't enough time to go through them one by one.
I mean, how come the plane doesn't interfere with my phone?
And why don't the other phones interfere with my phone?
I just always leave my phone on and nothing happens.
That is...
You can't!
It's just a phone.
Everybody, no! All electronic devices have to be turned off.
I can't turn off my pacemaker.
Well, your pacemaker is fine.
It just opens up a whole new can of worms.
Airplanes are magic! Okay.
So I have paused the video. There is some other part to it, but the language used is not as per like Indian standards, not considered to be good. So those who are interested can search it on the new and listen to it. The last part is important. So,
Hey, my sister is pregnant!
So Now this is like what EMI EMC is all about. So all the students, I showed this video, because probably I assume that you would also be having these questions. And when you study, read, do practically handle the things and cases on ground, you will realize the importance of EMI and EMC. So relevance of EMI, EMC in the industry as well as military is like when we have a social setup, we have some laws, rules for the society to live in, and exactly for that same purpose this EMI EMC is there. Anything which has a moving electron has to have to be controlled by some EMI EMC guidelines. So for this purpose these EMI EMC standards are made, and standards are made because all over the world, across the globe, wherever lab is testing, it can test it with some laid down standards, the proper setup, and come out with the results. And result of one laboratory matches with the result of the other laboratory if the tests are performed with the same standards. Now, in this slide, you can see this. Suppose this is on side of our country, So in this control environment, we know we have a standard. We will be following this standard, and all our test and equipment are complying to those standards. So this is okay. But suppose we go across, we go to enemy territory, or we go to some country where they have a different standards as NATO bloc countries, the US allies, European countries, and the erstwhile USSR countries. They generally have different standards. The US standards are available freely on the net, but generally the Soviet, the Russian standards are not like commonly available online. They call them as, I think, ghost standards. So like you in this slide, top right, may you see an environment, a military environment. See how many transmitters are there, what all equipment are like working. And in this kind of environment, if we don't have some law, some order, then how would the devices would be working properly? Hence the relevance of EMI, EMC. Down below in the left side, I have put a photo of an assembly line. So in this assembly line, these robots are working. They are not mechanical. They have a lot of electronics, sensors, and everything, positioners. They are all electronic systems. Suppose there is a minor fault variation in one of the devices, and what it will amount to in this assembly line, maybe constructing a very high-end car, and what will be the results. Hence the relevance of EMI EMC in the industry as well as military. When I say industry, there is a relevance of EMI EMC in the domestic like household built up areas also, because a lot of medical devices are being used, and all those medical devices are like, some of them are life-saving like kind of devices, and their proper functioning is very important. Suppose there is an X-ray machine and there is a dosimeter which measures the dose of as to how much exposure has been there. Suppose the device malfunction, then just think what kind of catastrophe it can amount to. Now in this slide, I have said here that, okay, when you are going to uncontrolled, how do you ensure that your device at least functions in that environment? Now that question is very difficult to answer, and that is how all this research and big like people come in. So this question which is there, what is standard when you are going to uncontrolled environment, is very difficult to answer. So the standards are made considering that in a battle space or wherever the like end use area, the end use area where we want our equipment to be working is having some kind of EM signature. And based on that EM means electromagnetic signature. So based on that electromagnetic signature, we decide on what standard to apply. Suppose there is a shield enclosure, and inside the enclosure we have to put certain EUTs, means equipment, means certain devices, LRUs, etc. We may not go for very strict, stringent EMI, EMC controls there. But if any standard is related to, like, suppose somebody has to work inside that shelter, then we have to take care of the standards which are required to be complied to for human safety. So that way. So as I mentioned, that we have, suppose we are sending a mission to Mars. Okay, so what standards do we have? We don't know what will be there in the Mars, in the outer space. We don't know. So even like these companies, Boeing and big they have their own standard. They don't share it in the open domain. Our, like, ISRO and all, they also have their standards. They don't publicize it. They don't share it in the open domain like that. So if we know the EM environment, it is very easy to decide on the standards. Where we don't know what would be the EM environment, it's very, very difficult to decide on what standard to apply for the device. The way out for this problem is to actually go on ground and measure the EM signature. So there are, like, it is a process. Militaries generally do it. Other agencies also do it. So US and NATO allies, they have these, like, bodies which analyze periodically, and that is how they improve on their standards which are recommended for EMI EMC compliance. Two standards are important for military: 464 and 461. 464 is system level testing, and 461 is a system, means subsystem or LRU level testing standard. So in this, like, now when you are designing anything, so you have to first decide this EMC standard. For what EMC standard I have to design? This is very important, because if you falter on this, then all your investment, money, time, effort, everything will go waste. Because once you have designed, it's very difficult to look for these compliance. You have made the PCB, multi-layer PCBs, you have fitted various filters in the cabinet, you have designed the windows, everything, and now suddenly it comes, no, it is not complying, and or maybe some other standard, then it's like very difficult. So first you decide a EMC standard, then you design a product. After designing, you carry out a test. During test, you will observe the failures. Now again, this is a place where wisdom comes in. Wisdom of working with the on ground, with the systems, clear reading of the plots and clear reading of the clocks which are present in the system. Those clocks may be digital clocks, the frequencies on which various microprocessors are working, various other digital signals, or maybe another switching waveforms, whatever. You have to have a clear like picture of that. So electronics background is a very, like, it's a must, I would say, for this part of the thing, and like on ground working. Now after noting these failures, you decide on the solutions. Now in my experience, when I have worked on ground, like, suppose there is a design issue, okay, and it has failed, it's very difficult to help the vendor. But suppose the design, means in the sense design, I will divide it into two parts. The PCB, since electronics would be there, so PCBs are obviously be there. So if it is a PCB related problem, then it's very difficult to handle. But if it is like enclosure related problem, the proper termination of the coaxial cables to pigtails, windows, you should have honeycomb filters placed there. Those kind of solution do come handy. Maybe EMI filters can also be used if one can like see. In one particular trials when I was handling, so the vendor was very intelligent. What he had done is he used ferrite beads core and a bag. He made a bag and he put it around a faulty device. So he was just trying to escape the trial process and get the certification. But since it was a temporary measure, it was not part of the original design. We like failed the equipment when we were doing the testing. So this EMC solution, it comes with experience only. Like when you have already designed it, you have finally your product is there, and then you want if you want a solution, then it is very difficult. But definitely in the cycle of designing and finally fielding the product, this happens. You design, you test failures, then you think for the EMC solutions, improve, harden the equipment, and then again means go in for redesigning, again test failures, like that. This I've already touched upon, as to like deciding on what is standard is very, very important. From like going on the drawing board, before that you must be very clear about the standard, in what environment your system has to work. If it is known, good. If it is not known, you go physically and measure it. And you have your like, then you give it to your design team. Now this part, when designing is over, generally at this point I have touched, there are no solutions. Good knowledge and tools. If it is enclosure level, like tricks, some filters are required, grounding is not there, proper termination of coaxial cables, etc. Sometimes the knowledge of the standard also helps. This I'll cover when I'm like I'll be coming to defense procurement. So one should be very thorough as to what all like is available to me. If one knows, one can still like tweak certain things and push the thing further. Now few case studies I'll touch upon quickly. This is HMS Sheffield. On YouTube all these things are available. If anybody is interested, you can go through the detailed videos. So in this, basically Falkland Wars, this HMS Sheffield was UK ship and it was fighting with the Argentinians. So Argentinians means they had certain inputs, some intelligence. So I don't consider them to be that high. Some third country actually helped them and like told them. So EMI, EMC monitoring is not only done on the ground. People do it from higher up above, from the space also. So with that, they came to know that their radar is switched off for certain period of time, and then again it is switched on. And this was being done because there was an issue of EMI, EMC interference. And I don't know, even when they were knowing it, how they commissioned the ship. That is again, doubtful things and debatable things. But this was the fact. So when they used to switch off the radar, and then they used to transmit. So this window was noted, and this was passed on to Argentinians. And they, during this window, they launched Exotech missile. It was French made, and it came and hit the ship, and ship sank. Now this again another this is again a good study. Basically case study involves other things. I'm just touching because time also we have to take care. So in this particular aircraft, it was a very good aircraft. It was used in operations also. But somehow when they flew very close to a transmitter, radio transmitters, they had accidents. So then it was analyzed and it was found that there is a EMI, EMC issue with the aircraft, basically the real tail part of it. I've highlighted this. So when the transmissions were there, the aircraft's electronics used to malfunction. Software also means used to malfunction because of the hardware. And all those, whatever was happening is like written on the view file. And because of this real, this tail thing, the Hapter used to take a nosedive and then used to crash. This, I found some case studies from the NASA site. So this Severomorsk disaster, it's a Soviet Union like explosive depot, and it caught fire. And it was concluded that it happened because of there was one over the horizon radar. Over the horizon radars are like big radars. They look flat towards the space, and they cover like almost outer space, so those very big radars were there, and because of their emissions, these ordnance fuses and all, they got exploded. Then I will come to this last one. This is interesting that early ABS system. ABS is a system which is fitted in the wheels to not let the brakes get locked. If brakes get locked, the vehicle will skid. So they had a EMI problems, and accidents occur when the malfunction, and then thereafter, like, it was improved. This is related to similar thing only, Mercedes-Benz case. So in Germany, there was a one particular patch of the road where these cars used to have malfunctioning of their brakes. So after a study, it was found that there is a transmitter nearby. Because of its transmission, the brakes are getting jammed and causing the problem. So initially they fitted a shielding screen kind of thing, and later on they improve the brake system so that it functions properly. This is also important, like this is talking EEG machine. In this, like, because of the EMI EMC, the EEG signals of the human body could not be listened at all, and it happened because of the interference from a local AM radio. And ambulance heart monitor and this defibrillator. This equipment was placed inside the ambulance, and the operator, like the nursing assistant who was there in the ambulance, he tried to call hospital, informing about this thing. And when you used to switch on and used to go on the call, this system used to heart monitor used to stop functioning. Because of this, the patient died, and the study was attributed to the EMI-MC problem because there was a big antenna placed on the rooftop of the vehicle. So this is another case study. This I have taken from, this is like, I'll go through fast. This RCI Hyderabad scientist, the names are mentioned on the view file. So this particular unit had 5 sub modules, all electronics modules. So it was giving EMI issues. So they studied it, and they commented as to how to control it. This I have taken specifically to incite the desire in the students, of this EMI-MC study. I was requested for to cover and some such. So the quality of graph is not very good, but these lines are as per the standard line. These are straight lines, and this is in the conducted part of the testing, conducted emissions. So we can see that when the EUT was tested, it failed. All these are different sub modules, all the 5 modules, these all failed miserably. Then further it was studied, and they found that power supply and command unit, it had a means because of this the problem was happening. And the starred paragraph is important, that the source of emissions was identified by studying the frequency spectrum. Now this point is very important. When you see at the graph, if it is the it may be the the main frequency, or it may be the harmonics. So one should be guessing. That is how you need to know about the system clocks and everything, and you can catch the point here. It is found that most of the emissions are present because of the DC converter switching frequency and its harmonic, which is the power source for EUT. Here it is UUT mentioned, but it is equipment under test. Significant spectral components of 10-700 megahertz were present. This is okay. This DC-DC converter module was not enclosed or mounted in a separate metallic enclosure, and EMI filters were not used on input and output lines of the power converter modules. Power cables used was not a twisted shielded pair. Other cable shields were not grounded properly, neither through connector nor through pigtail extensions. So in my experience, when I have handled EMI, EMC trials, the last bullet is very important. I have seen, even a very big companies faltering on this point. The coaxial cable is like correctly terminated on the connector on the panel of the EUT, but when it comes to the like PCB, it is not terminated properly. Only the core is properly soldered, but its shielding is like left like that only. So this problem I myself have noted in many these EUTs. And the second unique handling this processor unit. So this third bullet is important. The continuity when checked between the PCB ground and the EUT chases, which was showing 2 to 4 ohms, which was obviously very high. And there was no provision for the unit ground. I just cannot imagine how somebody designed it. The complete EUT was coated with non-conductive paint. So these are like basics. If your basics are clear, probably one will not incur these kind of faults. So whatever is taught, even a small thing in the basics are important when you are designing your system. Command and control unit, the EMI filters mounted on the chassis were not properly grounded, which was showing high DC resistance to ground. Input and output lines were getting crossover, resulting in mutual coupling between input and output. This is again a very common, like I would say, very basic thing. In the laboratory, one would give this kind of problem, as the experiment. So designing time, one should be very mature. Cables were routed haphazardly inside the unit. Definitely, you have to properly lay out the cables because the current, like the uh, cable shields were not grounded and left open at both the ends. This point again, this I myself have seen in many like EUTs, the system which came for testing. This problem I myself have noted. So all control manually adopted. What they did was all chassis mounted and PCB mounted AC converters used and closed in a metallic enclosure and fixed on chassis of EUT. On the chassis, they mounted these things. And low pass EMI filters like pi section, was incorporated. Wherever possible, the filters type ITNA were enclosed in a metallic enclosure and mounted on the chassis of the EUT. Proper grounding of filters was ensured by measuring the ground impedance, which was less than 100 mega ohm. Yeah, so there is a difference between earth, ground, so one should be absolutely clear about it. There should not be like doubt in that. Twisted shielded pairs are used for power and signal lines, and both ends of shields were grounded. Very, very important point. Crossover inputs and output cables was avoided by routing them separately. Cable hazards was routinely very close to the body of EUT to minimize capacitive coupling. Separate power input and output connectors were provided wherever possible, and separate ground point on EUT chassis was provided. Again, a very important thing. Unshielded external cables were replaced by shielded twisted pairs. Non-conductive paint of UT was removed to get more surface area and good ground contact to the ground plane. Proper grounding and shielding of internal clocks were ensured. So after all these measures which were highlighted before, these were the results. It came down to the almost acceptable limits. Now I'll touch upon my last part, that is defense acquisition procedure. So this is in the open domain. This document can be accessed from the government side, Ministry of Defense. And when in the army, in the defense forces, the everything like whatever is there, the main point is general staff qualitative requirement, that is referred to as GSQR. Now these GSQRs are like initially made by the users. They generally prepare the like what is their requirement, what range may the equipment should fire, how it should fire, all those capabilities, what should speed should be there. All those things are like converted into black and white by the users. Then this document is also like DGQA is basically Director General Quality Assurance. So environmental related, all the quality related aspect, they give inputs. Then it is the EME. EME is basically maintainability advisor. So they advise as to how much time it should take to open a thing or close the thing, or how much time it should take to assemble a thing or deassemble a thing. Basically, when it comes to repairs or maintenance, what times are permissible. So that part is like given by them. And EMI EMC is, there is a body. Every service headquarter, Army, Navy, Air Force, both have their one like body organization which like gives these EMI EMC requirements based on the anticipated EM signatures in the various fields. And the DRDO also is pitches in, because whatever they have, whatever they don't have, all those things are like taken input from like DRDO. Then finally, when this document is prepared, that time, if the user unit or the procuring directorate, if they want, they can float a RFI. RFI stands for request for information. In this, basically a ground work sensing is done as to what is available on ground, what all like we can get. We may be asking for moon, but somebody should be there to like give it to the procuring agency. Then these documents are put up for acceptance of necessity, and once the acceptance of necessity is approved, and with the AON there is a something known as detailed project report, these both documents are approved, then like it is floated for RFP. That is basically the tender. So yeah, all these things are there, but government holds the right to veto all these things and directly go in for procurement. Now this is from the procurement manual. Now they have changed its name to defense acquisition like document, from procurement procedure to defense acquisition document. So like in this EMI, I'll be now touching about EMI EMC part only. So whenever equipment is taken into armed forces, if it is a major weapon system, it is put through trials. Trials are basically evaluation done by the various agencies which give out their requirements, as I showed in the previous slide. I'll show again later. So EMI EMC is also spelled out correctly, and EMI EMC trials are also held. Certificate of conformance are also like accepted, but it has to be accepted by in the AON and RFME. Clearly it should spell out that certificate of conformance will be accepted from the vendor. So with this, if the vendor is clear while developing his product, he can keep testing his equipment and be ready with this documents. The laboratories have to be NABL/internationally accredited government design labs. Only those certificates are accepted. Technical bid, yeah. So whenever the technical bids are submitted, all vendors are required to submit all the whatever test or whatever COC certificate are there. It is good to submit it in the technical bids, so that the acceptance test procedure can be finalized based on that, and they can proceed further. Now the EMI EMC trials, as I mentioned, there are five. Fifth one is on applicability basis. These are primarily 4 trials. User trials, it is done by the person who's going to handle the equipment. Technical trials, this is done by the quality assurance people, about like in this much, so much of rain, so much of dust, so much of temperature, it will work or not. Maintainability evaluation trial, that known as MET, that is done by the agency responsible for maintaining the equipment, like within this time, like suppose can we change the engine or not, like that. Electromagnetic compatibility, this is EMI EMC testing, and security testing is not applicable to all, only communication systems have this. There are certain cases where the trials are also not applicable, And for that, but it has to be clearly spelled out in the initial state only when the acceptance of necessity is done. They apply for procurement cases where there is no product. Yeah. So NC means no cost, no commitment. So field evaluation trial / no cost, no commitment trials will not be applicable for procurement cases where there is no prototype level for the conduct of NC trials. Because like somebody is developing a new product and it submits it to us, it is not like submarines are already made and kept in the yard. You go and select, oh, I want this submarine and I'll buy it. No, not that. So for such cases, this is applicable. Or like suppose there are COTS equipment, these Wi-Fi routers, and if they have to be used somewhere, for that also those certification are accepted, and we don't put them through these EMI trials. Their simulation-based trials are all acceptable, as mentioned in here, but this all has to be like approved in the AON initial stage. Trial wing teams. So whenever the equipment is procured, the army makes a teams of like all the agencies. They put them under one team, and then it is responsible for carrying out the complete trials. Now EMI EMC evaluation is done by this as highlighted here on the view file, and they do the EMI EMC evaluation. Now there is also a scope of vendor premises evaluation. The teams goes there and evaluates the systems. Confirmatory trials are generally done when, like, suppose all vendors who have fielded their equipment, their all equipment fail. Then the government decides on like confirmatory trials, and they all can be given a chance to do something, some modification, and come again for confirmatory trials. This is okay. Validation trials, again, important thing. Validation trials are usually done on prototypes set during design and development or equipment being inducted for first time in the service. So if there is a new equipment, first time somebody is like army is inducting them, so then go for validation trials. So yeah, so I have finished. If there are any questions, I would like to answer to the best of my capability. Or if people want, I have some slide on anechoic chamber that also I can like cover. Thank you.
Thank you, sir. The forum is open for discussions, if any. I don't see any queries posted in the chat box. So the participants, if interested, can unmute themselves and have a talk with sir. Dipti, do you see any queries? I don't see any, Dipti. Dr. Dipti?
Yes, ma'am. Any questions, if there is?
I don't see anything on the chat box. However.
Okay, sir. So, sir, thank you so much, sir. Actually, sir was skeptical regarding his, how to plan his talk when after the talk by Mr. Satao from RCA.
Yeah. Yes.
He was so, that shows how, how we should also learn and adapt. He was so gracious enough to call me and ask me what in fact, what he said was that he presented whatever I was planning to, was the kind of opening. And I was really surprised and impressed with his honesty with which you mentioned. And I see that you had so much, you made it very interesting so that people would listen to you and try to understand. And I hope this kind of interaction with you is just not, it's just the beginning. Hope we can have more such in future. And if you can share the slides with me, I can, is it possible, sir? Can I have the slides?
Yes, ma'am, I can share these slides. slide.
So I will share with the rest of the participants, and I think sir's email ID is also shared here. So if there is any more questions, okay, I think we can come to the end of the session. So thank you so much, and we'll have more better interactions or more interactions in future.
Yeah,
so,
thank you.
Ma'am.
Are we waiting till 5 o'clock, or are we going ahead?
I think Thomas Uti sir, are you there?
He's online, yeah. He's there online, I suppose.
So, yeah, should I stop this thing or?
Yes, sir, it would be nice, and if you could share the slides with me, I'll share with the rest of the participants.
Yes, ma'am. Okay. Thank you.
Thomas Uti sir, if you are there, can you please respond?
Yes, Deepti.
Okay, sir. Sir, do you mind starting because we are a little just 10 minutes ahead of time?
No problem. We'll start.
Okay. So meanwhile, I think one question has come up. Anu Muhammad has mentioned, it's a comment, I guess, that practical experience really required in the EMI EMC. Of course, that is what sir's talk had been like. Thank you, sir, for your presentation.
Yeah, thank you.
Yeah. Thomas Uti sir, can you share your screen?
Okay, I'm sharing.
Vinupal ma'am, can we start with you?
Yes, Deepti.
Can you see my screen?
Yes, sir, it is coming up.
It's not in the slideshow mode, you can see it.
Yeah, that's it. Okay, I think it is fine now.
Yes, sir. Good afternoon, sir, and once again, welcome to this session. Let me introduce you to the participants once again. Dr. Thomas Kuti is an associate, Thomas Kuti Matthew by full name, is an associate professor in the Jitam School of Science, Jitam University, Bangalore campus. And he holds a doctoral degree in microwave electronics from the Department of Electronics, QSAT. And he has worked from 1999 to 2019 as a faculty and research guide in the School of Technology Applied Science campus of MG University Regional Center in Kerala. And he has guided over a dozen PhD scholars in domains like RFID, antennas, wireless sensor networks, to name a few. And from 2006 to 2008, he worked as a postdoctoral research associate at the Department of Electronics in the University of Kent in a Franco-British collaborative project. He has also served as a consultant in various industries on the EMI, EMC aspects of RFID deployment in UK. And he has undergone several courses on EMC related topics at the University of Oxford in UK. With this intro, over to you, sir, for a session on active probes for electromagnetic near-field measurements. Over to you, sir. Thank you.
Thank you, Vinupal ma'am, for the introduction. And I'm very happy to associate with the Department of Electronics for this EMI EMC workshop. And thanks for the organizers for giving me an opportunity to give some of my experiences in the little bit of experience in the field of EMI and EMC to the students in the academic. My talk is mainly made in the academic point of view. I am not from the industry, and mainly it should be benefit the students who is studying in the MSc and PhD. They should be getting attracted to EMC and other related subjects, and they should take up these type of works in the future. So we will move to the presentation. So the topic of my presentation is active probes for electromagnetic near field measurements. And I am an associate professor, radio and atmospheric sciences group. We have recently started And Geetham University has 3 centers, Visakhapatnam head office, then we have Hyderabad and Bangalore campus. And we are concentrating on research in a big way in the Bangalore campus. And our institution is also great. So coming to the outline of the presentation, first we will see the background of the presentation, why we are going for these near field probes and other things. And then what is near field? We will be explaining what is near field and far field. And near field probes, what is a near field probe? And E probes and H probes, electric field probes and magnetic field probes. We call it as E probes and H probes. And near field scanners, that is very important. How to get, for example, if you are on an IC, how to get the electromagnetic emissions from over the IC. Very small, very high resolution near field scanners are there. Then active near field probes. What is an active near field probe? What is the importance and why we are going for active near field probes? And I will give a brief overview of the Franco-British collaborative project on, which is called APMAN. Which is mainly to design active probes for electromagnetic near field, which will be for many practical applications in connected with ERC in Europe. So after that, we will be going to the conclusions. Now, coming to the background, we know what is electromagnetic interference. All the people, very experts, people in the electromagnetic and interference EMI field have already explained that. But I will just give a brief introduction. So rapid increase in electronic devices in all areas of engineering, technology, and consumer products we are observing. And these electronic systems have high level of integration, decreasing sizes, and increasing frequency. And here you can see an electronic device. Nowadays, we have got a microprocessor, microcontroller, and you have a lot of devices in your mobile phones. All these devices, day by day, it becomes more. And at the same time, you will be having a lot of emissions, which is coming from these electronic devices, which can be already explained like radiated interference will be there, radiated emission will be there, conducted emission will be there, and conducted interference will be there. So this is all you are discussing during the all experts have already explained all these things. Now, some components generate electromagnetic interference problems, and the complexity of these devices can reduce the efficiency of each function. Now, because of this, there will be risk of failures due to EMI. Because of the electromagnetic interference, there will be a lot of risk of failures, and a new product, they have to go for the EMC test. Then only it will be getting, you can put it in the market. So a lot of standards, a lot of things are, I'm not an expert for dealing all this. Very good talks have already been delivered, and really most of the participants will be getting benefited out of that. And there will be impact on development costs because of that. And it is therefore necessary to use near-field measurements to characterize EMI problems. So to characterize, if you are looking at the low frequency, you have a lot of conventional methods like you are putting some filters, a lot of things. That is at a very low frequencies. But if you are going to high frequencies, because the electronics is going, your chips are going to higher frequencies, your wireless communication is going to 5G, is going to millimeter waves, like that. Electromagnetic interference problems are going to very high frequencies. And because of that, the wavelength is very small. When the wavelength becomes very small, we have a lot of problems for measurement and everything. That is the thing that we are concentrating. Effective measurements of radiated emissions need calibration of the probe. You have to calibrate. Once you make a probe, it has to be calibrated. An understanding of the coupling mechanism is necessary for choosing an appropriate probe for near field measurements. So this is the background. So what is the importance of probe? I have just explained, not going to EMI and EMC. What is the importance of the probe? Different type of probes. You will be having some type of probes at very low frequencies and entirely different probes at a very high frequencies. Very difficult to fabricate because it is very small, depending on the things which I have explained. You should have an idea of what is meant by a near field and far field. This is many of the experts here may be knowing very well, but looking at the student's point of view, and it's just a recollection of the things what we have studied. And we can divide, suppose there is an object which is radiating, near to that, lambda by 2 pi, lambda is the wavelength, lambda by 2 pi, which is 0.159 lambda, you have the reactive near field. You have the reactive near field. And our work is mainly, we will be having probes very close to the PCB, which we will be dealing with the near field, reactive near field. And from that point to 1 lambda, up to 1 lambda, you have the radiative near field, and you have a transition zone. After that, a transition zone, or you can say it is a far field. After that, you can say transition zone, and after 2 lambda, it will be far field. And some books, a little bit of difference will be there depending on the antenna point of view and other things. So this is very important. This concept of near field and far field is very important for a person who is doing EMC. It's very, very important. So you have to keep in mind these values, lambda by 2 pi, lambda, and far field is after 2. Now, an idea for the student's point of view, I am just putting, this is a very simple thing. We have the electromagnetic spectrum, we have the increasing frequency, and we have the decreasing wavelength here. And at low frequency EMC problems, when we are dealing, most of the conventional EMC works are at very low frequencies where we can see it is very high wavelength. So the treatment and other things are entirely different. So you have 10 meters at 30 megahertz. Most of the problem we encounter around 30 megahertz, 10 meter is the wavelength. But if you come to the latest problems, for example, your IC, your processor, your microprocessor have a clock frequency of 3 gigahertz, and you will be having the lambda with the emitted radiation will be having a wavelength of 10 centimeters. So this picture you have to keep in mind. This is very important, not only for EMC, EMI, when you are doing any person who is dealing with the any time, you should keep in mind these values in your mind. This is a please, only for the student's point of view, I have given all these basic things. Now, looking at the 300 megahertz, suppose you have a radiating source at 300 megahertz, lambda equal to 1 meter. Let us have a reactive near field. What is the calculation? Lambda by 2 pi is equal to 15.9 centimeter. Less than that, it is a reactive near field. Radiative near field is less than 1 meter, and far field is over 2 meters. So here we are putting antennas and measuring over far field. We are putting different type of antennas, and we will be getting the EMI emissions. But the thing is that you cannot identify the source of emissions at far field. You can see that, for example, a car. When a car is, before it is, my collaborator, when we are going to, they have a car in an anechoic chamber, and they will be putting it into treadmill, and it will be at different speeds, and there will be electromagnetic measurements will be taken. It is in the far field, and they can identify how much is the emission that is coming like that. That is a far field, this one. But we are interested in near field because we are interested in like ICs, microwave circuits and other things where the radiating source you have. For example, if you are working with PCB is something like you can have reactive near field. You are making the measurements. You are putting a probe and you are putting over a particular place. Then you are seeing some field. You are working with the reactive near field. But in the case of more high frequencies, if you go to high frequencies like 3 gigahertz, the wavelength is 10 centimeter. If you calculate C by F, you will be getting lambda equal to 10 centimeter. So you see the reactive near field is 1.9 centimeter only. And the radiative near field is less than 10 centimeter, and the far field is over 20 centimeter. So this picture you have to keep in mind. When we approach the EMC problems at lower frequencies and higher frequencies, this is very, very important. What is the reactive near field, and what is the radiative near field, and what is the far field? Now coming to the radiation. Suppose you have a source, suppose PCB is radiating. How it is radiating? The instantaneous change in current flow causing magnetic field. You know, when a changing current, it will cause a magnetic field, and the radiation will be coming out of that PCB. and instantaneous change of a potential difference, it will cause an electric field. So this is a basic concept of the radiation. But the thing is that when we are coming to near field, that is important, a change in voltage will cause a change in current and vice versa. One of these vectors will predominate. At near field, at a reactive near field, one of these vectors will predominate. That is determined by the impedance of the radiating surface. If the impedance of the radiating source will determine whether predominantly magnetic or predominantly electric field is produced. You can have electromagnetic field radiated because of these two mechanisms. And whichever is produced depends on this the impedance of the radiating source. That in a PCB, a particular thing, whether it is producing an instantaneous change in current or instantaneous change in potential difference is very important. And you can have an emission source like this, lambda by 2 pi. You can see lambda by 2 pi is the reactive near field. Up to the reactive near field, you can see initially you cannot observe E by H, electromagnetic wave. The wave impedance E by H is equal to 377 ohms. Okay, in a free space. But you cannot observe that. The electric field and magnetic field will not obey all these things. And if the impedance is low, the H field, the magnetic field will dominate. And if the impedance is high, the electric field will dominate. And after that, it will be coming, and after that, you will be having 377 ohms. This is in terms of the wave impedance, what is the reactive near field and what is the H field. And the thing is that when we are going with a probe here, the important thing is here you will be getting electric and magnetic fields. It is an electromagnetic field. But here you will be getting only electric or magnetic. Suppose a loop antenna, near the loop antenna, very near to the loop antenna, you will be getting only the H field. That will be dominating. So this concept is very important as far as the probes and probe designs are concerned. Now coming to the concept of near field probes. The probe designer has to concentrate on a different concept than antenna. Probes must be designed to measure electromagnetic field with minimal field perturbation. The probe must be electrically small as possible. Why? Suppose you are going to near a PCB, if you are putting a probe, it should be very small, like I'm telling. What is the reason? You look at the simulation. I have a microstrip line. I have simulated in CST. You can see this is the electric field at the center. It is high. It is like this, and you have the electric field variation. And I am putting, this is the simulation which we have done. And we have our probe. We are putting the probe near to this, and you can see the field will be getting perturbed. The field, the probe has an influence, and the field will be getting perturbed. So because of that, in the near field measurements, normally in our near field measurements, we are putting above 1 millimeter, 2 millimeter like that, very close to the IC or very close to the circuits we are putting. So we have, later I will show you how we are doing that. So this is the way, the things you have to see. A near field probe, when you are putting very near, it produces some perturbation. Because of that, you have to apply some kind of probe correction. There should be, suppose what you are measuring, it will not be the exact field, but there should be some probe correction. That itself is a lot of work has to be done. My colleague David Baudry in France, he has done excellent works in that field. His PhD is also in that field. And a lot of work for probe calibration and compensation has to be done. Now, the design of the probe is different from that of an antenna. And the antennas are designed for maximum coupling to the electromagnetic field. When you are designing an antenna, the gain, you are looking at the gain. If you don't have any gain, people will say that your paper will not be accepted. People will, why, what is a gain? But probe should be, the electromagnetic antennas are designed for maximum coupling to the electromagnetic field, but probes are just opposite. A probe designer focuses on enhancing the sensitivity and spatial resolution, discriminating unwanted field components, and on obtaining slow impedance variation over the operating frequency band. We will see. So it is difficult to enhance the sensitivity and spatial. We will see, because if you sensitivity means you have to pick up more power. When you try to increase the sensitivity, your probe will become larger. It will be high. So there should be some compromise between these two. Here comes, if you want to increase, if you are designing your probe to be very small, there should be some amplification. That is why active probes are coming into picture. You have to use the active probes so that you can use a very small probe. The sensitivity also can be increased and the spatial resolution also can be increased. And this is the probe design dilemma. And you have a size and you are looking at the spatial resolution, you are looking at the sensitivity, you are looking at the distortion produced due to the probe, and the directivity, bandwidth, all these things are a big problem. It is very difficult than an antenna. I can design an antenna very easily, but the probe for a particular, in general, you are seeing a lot of probes like loop probes and other things. But a practical application at high frequencies, if you want a near field probe, the design, you have to be very, very difficult. You have a lot of experience and a lot of electromagnetics, and also you have to look at the application that you are going. The probe should be specific to the application that you are going to use it. So that is the thing that you have to keep in mind. Choosing the correct probe is determined by whether the signal is electric field or magnetic field. I told you, near to a radiating source, it will be primarily electric field. In that case, we will be using a coaxial monopole probe. Coaxial monopole probes will be measuring the Z component, the vertical component. So because your probe, you will be having the center part will be extending and it will be getting the vertical fields. And a dipole probe is like this. So it can measure in X direction. If you put, you will be getting the electric field in the X direction, and if you put in the Y direction, you will be getting the Y component. So to characterize fully, you need many probes, not a single probe. A single probe will give only one component of the electric field. To characterize a circuit, you need both electric field and magnetic field, and also many components also. If the signal is primary H field, use one of the loop probes. If unknown, suppose you are given a circuit, you don't know what is the predominant. So you try both. You have to try trial and error, and you have to identify. And initially you will be using a bigger probe, and you will be identifying some location. Again, you have to use a very small probe, and you can identify the things. And in our works, we are not doing these identification. We are just scanning the project which I have in. Any circuit, complete scanning will be done with a very high resolution, and it will be taken at a micrometer resolution. The electric field and magnetic field will be picked up. Now, conventional electric field and magnetic field probes. You are all familiar with these type of fields. The electric field probe, electrically small monopole or dipole. Very simple. You can see, you take a 50 ohm coaxial cable, small one, semi-rigid coaxial cable, and you can extend this. If you don't extend it, then also it will work. It is called open-ended coaxial probe, and it will pick up the electric field. If you increase the length, it will pick up more electric field. Okay, so that is the electrically small monopole probe, and it is basically the impedance is capacitive, and it will pick up little bit of this little bit of magnetic field also. If you want to, at some frequencies, if you want to reduce it, you can put some modifications for this ground, the shield, and you can reduce that. Now, this is a dipole probe. I told you, if you want to EX and EY fields, you have to use this type of probes. And H field probes, electrically small probes, input impedance is almost inductive. And this is a central wire you take and you solder it to the outer shield. It becomes a H field probe. So these probes are very common. All people will be using all these things, and a very common thing. And this is some of the probes which we made for the magnetic field. So whatever be the shape, it will pick up whether these type of probes and many probes. One of the probes we have used for EMC scanning. And more about these H-field probes. What are H-field probes? This is a commercially available H-field probe. All the H-field probes, we will be putting a notch here. Because these H-field probes will be, these probes are highly sensitive to H-field while being relatively immune to E-field. Each H-field probe contains a single turn shorted loop inside the balanced E-field shield. This is the balanced E-field shield. You will be, you can just, because this one is not having a shield. But here you can see the conductor, center conductor is coming like this, and it is soldered here. And also the outer shield also it is coming, and a notch is given, and which is to reduce the E-field coupling. Okay, that is the case with the H-field probes. So you can construct using a semi-rigid coaxial cable, and you can make it like this. And there are different type of constructions are there. You can available. And this is one of the constructions by which you can very easily and most of the probes available in the market, you will be purchasing from many vendors, and most of the probes are of this type. And then a notch is cut at the high point of the loop. This notch creates a balanced E-field shield of the coax shield. The loop rejects electric field signals due to the balance shield. So this is all about the H-field probes. Now, I just put, for your information, I am just giving analysis to some probe near field sets I have given. I have taken from their site, and you can see the H-field probes. It is 6 centimeter. 6 centimeter H-field probe is having a E/H rejection of 41 dB. You can see the upper frequency. You can use it up to 790 megahertz, 790 hertz, because all these probes are used below the resonant frequency. You cannot go up to the resonant frequency. Okay, so when it is 6 centimeter, the resonant frequency will be less, because lambda, you looking at the lambda, it is 6 centimeter. The resonant frequency in terms of lambda, it will be larger, and you will be having the lower resonant frequency. Suppose another one, still smaller probe we are considering, 3 centimeter probe. It is a H-field sensor type, and you will be having 29 dB E/H rejection, and also 1.5, it will go up to 1.5 gigahertz. You can see the resonant frequency, the maximum frequency, upper frequency is 1.5 gigahertz. And still smaller, if you are using, just 1 minute. Yeah, still smaller one, it is 1 centimeter. You can have a 1 centimeter loop, and you have 11 dB rejection, and you have 2.3 gigahertz maximum upper frequency. So you can see that the probe size decreases. Also, the sensitivity also decreases. As the probe size decreases, the sensitivity also decreases. So that is the problem. So if you go smaller and smaller, the sensitivity also reduces. And these are some probes, which is the bolt probe and the stub probe, which is given by this field. And coming to the coaxial electric field probes. Coaxial electric field probes, you can have a different type. We have an integrated circuit. We can put a coaxial electric field probes over it. The advantage is this is having, the tip is having, you can get very high resolution, spatial resolution you can get. So it is very good for this type of integrated circuit scanning and other things. And the inner part of the coaxial cable acting as an antenna. This is a coaxial cable, and the outer is the shield, and this is the insulator inside, the dielectric inside, and the external coaxial cable connected to the ground. This is called the EZ probe. It can measure the Z component of the electric field. And coming to the EZ probe with minimum antenna, so you don't have the extension. This is called open-ended coaxial probe. So very short antenna to minimize the capacitive coupling. So we will go for some mathematical treatment where we will be computing what is the capacitive coupling when we are putting these probes over a microstrip line. So you can minimize the capacity coupling. But if you go for the EZ probe with the enlarged plate, the enlarged ground plane reduce the parasitic currents on the cable. So you can EZ probe, some probes you can see they will be putting a plate like this to reduce the parasitic currents on the cable. Now, these are the differential EZ probe. The differential EZ probe, 2 cables are taken and they will be having 2 antennas like this, and the differential probe and the differential EX probe. Suppose you want to measure the X component, we have the differential EX probe. Then ground plane, here we have the strip line version, the strip line version of the probe, and here is the ground plane, and this is a 50 ohm adapted strip line. So different types of probes are available, and now we are going to see how, because most of the coaxial in near field scanning we will be using this type of probe, simple probe which can provide high resolution, and in that case we are going to see how when it is scanned over a microstrip line, how the field is varying. For that, the monopole probes used for the near field measurements are meant to collect voltage proportional to the local electric field EXY at the measuring point. The probes are generally very small size compared to the operating wavelength and is in the far off resonance region. It is in the far off resonance region, I told you. Now, monopole probes are widely used for mapping normal electric field, but it also picks up tangential components to some extent, which depends mainly on the tip length and dimensions of the probe. A proper selection of the tip length is important to produce good suppression of the unwanted components. So you have to select, depending on your particular application, you have to select a probe which a particular type of tip length, then you will be getting, you can simulate in the CST and see how much it will be picking up. Now we are going to put the monopole probe over a microstrip line. You can see this is a microstrip line and we are just putting it over the microstrip line. So at this point, suppose you are having the V out we are getting, and S21 is V received divided by V transmitted. And we can define S21 as VR divided by VT. And this treatment is taken from the famous paper of Gao, which gives the mathematical treatment of this microstrip line, the monopole probes over a microstrip line. VT is the transmitted signal at port 1 of the VNA, and VR is the received signal at port 2. And you can see that the signals at various points are represented as follows. V input is the input signal to the microstrip line, that the device under test. V out, the signal, the output signal at the monopole probe, and VXY, the signal at the scanning point. EXY is the signal at the scanning point. And we can form the equations like this, the various equations based on the transfer function. Somebody, please, somebody is joking, disturbance is coming, okay. Where H omega represents the transfer function, and using the above relation, S21 can be represented as, depending on these different transfer functions, and S21 can be represented like this, and the H dut xy of omega is equal to S21 measured divided by this H cable 1, H cable 2, like a H probe of omega. So S21 is measured using network analyzer, knowing the transfer function of the probe, the transfer function of the DUT at XY, and whereby VXY can be calculated. Okay, this you can see the treatment is the famous paper, the old paper about the monopole probes in Gao, which is published in IEEE. There are different methods to find the transfer function of the monopole probes, from equivalent circuit modeling, from electromagnetic modeling, and from the calibration of the probe. We can find the transfer function from electromagnetic modeling also. Once you get the value from the simulation, you can go, you can calculate the transfer function and also the calibration of the probe. Now this is the equivalent circuit. This is the equivalent circuit of the monopole probe transfer function. And here you can see when we are putting it just above 1 millimeter or 2 millimeter above the microstrip line, there will be a capacitance between these two, the tip of the probe and the microstrip line. And we are considering another capacitance here and another capacitance between the tip and the shield. And with these three, we can represent the equivalent circuit, which is also a paper based on the four-series model. And with that, CTM is the capacitance between the tip of the probe and the microstrip line. And CTS is the capacitance between the tip of the probe and the shield. And CTG is the capacitance between the tip of the probe and the ground plane of the capacitance. And the V out, the output is given by J omega CTM into ZL divided by 1 plus J omega ZL into CTM plus CTS plus CTG, the various capacitances we have considered into VXY. The comparing equation 8 with equation 4, the transfer function of the probe is obtained as H probe is equal to J omega CTM into ZL plus 1 plus J omega ZL into CTM plus CTS plus CTG. The transfer function of the probe is composed of capacitances and are formed between the parts of the probe and the microstrip line circuit, that the device under test. A simplified model. So we can neglect some capacitance, and a simplified model can be found just taking CTM. If the major part comes from the tip of the probe and the microstrip line, the capacitance between the tip of the probe and the microstrip line. A simplified model of the probe transfer function can be modeled, and you can take the H probe as J omega CTM ZL into 1 plus J omega ZL CTM. CTM values of the probe can be evaluated from the S11 measurements. From the S11 measurements using similar CST. Once you get the S11 values, from that you can extract the values of CTM. Now we are putting the microstrip line. We are putting the probe over a microstrip line. This is very important in calibration. Most of the small these near field probes, we can use this for calibrating. Once you create a probe, it has to be calibrated. For that, you know the field above at 1 millimeter above the microstrip line, and you measure this, and with that, one of the methods for probe calibration is this one. You put it over the microstrip line, and with that you can calibrate. And we have simulated it in the CST Microwave Studio with port 1. This is the port of the microstrip line, and this is port 2 and port 3. And we can see the S11 variations we have seen. We can see it is in the far off resonance region we are operating, and we are moving like this. Suppose we are moving the probe like this. I am moving the probe perpendicular to the axis of this microstrip line. I am moving like this, scanning. Then you will be getting the variations like this. The power in dBm, we can see like this. And this is for different tip lengths, 0, 1, 2, 3, 4, and 5 mm you will be having. So you can see the power coupled to the probe increases as you increase the value of the probe length. So that is the influence of length. Here we are seeing the influence of the length of the probe of the center conductor. So if you increase, you can use open-ended coaxial probes. Also, you can use and with the center conductor extended to a particular length. Now, this is very sensitive to. We are just plotting it, the output voltage with respect to the probe length. I am plotting like this. The probe length we are plotting like this. So the voltage for different lengths of the inner conductor, it's the same thing we are just plotting. So that is all about the near field probes. above the microstrip line, and with which is widely used for calibration and which is widely used in near field scanning also. Now, coming to, suppose you are provided with a circuit, you have to characterize it. Okay, if it is a PCB, big PCB, you can go and just get the sources of emission by putting the probes like this. But if it is a very small, for example, an integrated circuit, IC, how you can measure, how you can find the sources of emissions in the IC? There is a separate, you may be knowing IC EMC. There is a book which is called now this type of measurements, separate measurements are, which is called a book is there, which is called IC EMC, the IC level, where you cannot identify without a setup with high resolution. Micrometer resolution is needed to identify this type of emissions from this type of material. So this is the near field scanners. The near field scanners with a resolution high enough to map the fields above the integrated circuit packages are very useful in EMC measurements. The direct technique involves coaxial cable to connect the probe to the receiver as shown in the figure. So you have the material here and the probe will be connected here, and this will be scanning with micrometer or a 1 millimeter resolution. It can move and it will automatically plot the field above the material, field above the particular device. Okay, so that is the near field scanner. Without near field scanner, you cannot go for EMCs at a very, very small devices. Just PCB you can do with the trial and error and other things we can identify, but it is very difficult. Here also, with one probe we cannot identify. We have to put, first we have to put the electric field probe, we have to put the magnetic field probe, like the different probes we have to use, and you have to get the information out of this scanning. And then you have to identify what is the field and what is the emissions and what are the problems associated with these devices. And this is the near field measurement test setup. I was working in a postdoctoral as a postdoctoral fellow in University of Kent, and we have the project, a Franco-British collaborative project, and this Rouen, France Research Institute of Electronic Embedded Systems. They are very, very good in EMC and what is called probe design and other things. And the person who was working with me, his PhD, he has many of the papers we can see. First reference is his paper, David Gowdry. So they have the setup. They have the setup, which is a mechanical features are 5 axis X, Y, Z plus 2 rotations. You can have 2 rotations. Resolution of X, Y, Z is 10 micrometer resolution is there, and rotations 009 degree. And the scanning volume is 200 into 100 into 60 centimeter cube. We have a scanning volume of 200 into 100 into 60 centimeter cube. So this is a instrument which is needed. With you cannot do EMC test and other things at IC level or very small devices, microwave devices, you cannot do. Now, at this point, what is active near field probes? You have a probe. If you are reducing the size, the sensitivity will reduce. Sensitivity also will reduce. Now, if you have the amplification, suppose you have an amplifier, a proper amplifier, then you can boost your signal, you can amplify your signal, and the sensitivity can be improved. But the problem is to get wideband amplifier is difficult. That is the problem. So for a particular application, when you have different probes, when you put, maybe it will be working at one frequency, it will not be working at other frequencies. So the active probe design, the major problem is getting bandwidth. And bandwidth over the required medium is required range is difficult. So that is the problem that is done. And for that, active probes with the balanced circuit configuration are suggested. Suppose you are having the probe here, you have the latch couplers, and you have the MMIC amplifiers, and which will be connected to the VMI. So this is called an active probe with balanced circuit configuration. This is the concept which we have used in that project. And the project is like this. It is between University of Kent, Canterbury, and IRSIM, which is in Rouen, France. And it is an indirect project by European Union. And the heading was active probes for measurement of electromagnetic near field. And it was the collaborators are at the University of Kent. We are having Freddie Koning, that is a research student who was working with me. He's from France, and myself, and John Batchelor, he's a professor there now, and he's also a faculty there, Adam Justice. So we are at the University of Kent, and we have David Bowdry, a Sohail. This is a research student, and he is the person we've done a lot of work in probes, and he is the research associate. And there is two persons like Annie Louise and B. Masley is the head of that institution. That is from IRSIM, France. And this project, I was working around 2 years, more than 2 years, 2 years and some 3 months I have worked. And finally, we were able to deliver the required things that they were asking. It is for some industries connected with them, with the European Union supported project. And just before going to that, this is one of the probes. You can see very small probe with A is equal to 0.52, B is equal to 1.78, C is equal to 0.25, and LZ is the extension. So I want to see the extension, how it is varying. With the extension, I am varying. These type of works we have done, extensive work on probes, different type of probes, and we have developed some probes. We are trying to develop simultaneous measurement of electric field, EX and EY, some particular type of probe. Because of the non-disclosure agreement, I cannot show that probe here. I will just simple probes I will be showing here. And this probe, you can see the output voltage for the normalized electric field. Normally, it will pick up signal. Okay. The EZ we are putting over this electric field will be picked up, but you can see tangential electric field. The EZ field will not pick up tangential electric field, but with respect to the tip length, you can see tip length increases, the tangential field pickup also reduces, even though it is small, but at some frequencies it will be a little bit significant. And you can see the tangential field pickup can be reduced by tangential electric field. And this is one of the probes. You can see this probe is an L shape. This will pick up the X component, Z component, and this will pick up the tangential component. And what happens is, if you look at the probe tip length, suppose I am having only without this, if I am having the tip of in this direction, this is length which picks up the Z component. If I am changing LZ changing, keeping LX equal to 2 mm, I am keeping constant. LX I am keeping constant. And if I am LZ, I am changing. You can see the probe voltage, the output voltage increases with the increase. That is the Z component. But if I am increasing, keeping the LZ at 2 mm and LX I am changing, I will be getting both components picked up at this point. Both the components will be there. Suppose you are putting this type of probe, and if you are rotating, always the Z component will be picked up, and the X component and Y component, as you rotate, at one point it will be picking up X component, at the other point it will be picking up Y component. And these type of things we have explored. As I told you, the real probes developed, I cannot disclose here because of the non-disclosure agreement. These type of probes we have used, and this is the measurement setup at the University of Kent. And this is not a good setup. We have developed servo motors and other things. Initially, we were trying with this semi-anechoic chamber was there, and we were measuring the electric field emission from these devices. And we are plotting the near field like EZ using the electric field probes. We are plotting EZ and EY fields. Now, our active probe design, the Lange coupler used is the 3 dB coupler targeted with a bandwidth of 0.8 to 3 gigahertz. Our required working for the project is 0.8 to 3 gigahertz. So we have used the substrate Roger 1.4 mm, epsilon R is equal to 3.2 with the surface mount devices and low noise MMIC amplifiers. And gain of the circuit is 17 to 25 dB expected. Good impedance and output return loss, and these are the variations. And here you can see the latch coupler. First we designed a latch coupler, and the MMIC, you can see the entire circuit, the OMMIC amplifier is put here, and the latch coupler, you can see there should be the bond wires to be connected in a latch coupler. Wire bonding is the process of creating electrical interconnection between the semiconductors and silicon chips using bonding wires, which are fine wires made of materials such as gold or aluminum. Suppose you are not perfectly bonding, bond wire technology is not exactly done, this will not work. That is the expertise. My student, my PhD student working with me was having, he was working in Japan in Fujitsu, and he is an expert in doing this bond wire technology. This some experience is needed. So here you can see the gold, this is the gold, the rod symbol 1, and it is coming and it is melting, and with that you will be connecting in the different points on these circuits. Here, this is the latch coupler, and this is the process which is going. You can see the gold things are coming. The gold is coming, and here is the, we are taking the gold from here, just touching here. And this is the latch coupler, and this is the design circuit. This is also gold plated. And here you can see the balanced amplifier circuit has the precise bonding and bond wire. And the final setup, you can see the designed one with MMIC, OMMIC and other things. And here we have expected range, but we got only 15 to 20 dB at 0.8 to 3 gigahertz. I told you the bond wire is very important, and we got 15 to 20 dB with these latch couplers and MMIC amplifiers. Here you can see the different loops and which is connected here, and this is for EMI shielding. It is connected in a box. It is placed in a shielded box, and we have the input and output. You can see. So this is again about 15 to 20 dB, and this is the measurement setup of EMC. And we have used this setup for all the measurements. Every month we will be going and we will be using it there with our collaborators. And this is the one of the setup, another setup where we are using in the development process. We have been using a parallel coupled microstrip line. A parallel coupled microstrip line is filter is used, and the field above that is measured using this one. And you can see this one, and different plots are plotted, HX and HY, and different are plotted. So with this, and this is done at 2.1 gigahertz at 1 millimeter. And this is with this, I will like to conclude my talk. We have discussed the concept of near field probes, near field and far field, and the various near field probes and characterization methods also we have discussed, and the concept of active and near field probes we have discussed, and overview of the AppMan project also we have discussed. And here you can, I just give the picture. This is the team, and this is John Batchelor of the University of Kent, and this is David Bowdley. He has done extensive work on probes. And this is Lester Law. He is from University of Sheffield, and this is the research student working with us in University of Kent, which is Freddie Koning. And this is Sohail. He is a research student at LC. And this is myself in the lab of the EMC lab, the final, after taking the final measurement at the EMC lab. With this, I would like to conclude my talk, and it is open for discussion and any questions I will see.
Thank you, sir. I have a couple of queries in the chat box. The first one is from Mr. Praveen. This is regarding the Andritsu slide which you had shown. I'll read out the query. For the Andritsu probes shown, after that high frequency limit, will the probe or the loop act as an antenna? In which case, can't it be used for radiated EMI pickup at those frequencies as well? Whether it will act as an antenna?
Yeah, it will act as an antenna, definitely. It will act as an antenna.
Whether it can be used for
Yeah, I
radiated
think
EMI pickup.
I never used it, but I have not at all extensively using for EMC application. I am not an expert in EMC. After the project, I am just concentrating on RFID, and I am just doing some works in RFID, EMI, EMC aspects of RFID. And I am not doing anything because I have great interest in EMI. After coming after my PDF, I came to India because my institution that time was not supporting research. And EMI, EMC work, as you know, it a lot of effort, a lot of money, everything should be there. So it was not permitted. Actually, I have given the work for one student, and we dropped it. It needs a lot of effort, and so that peace of mind we will not get that university. So I dropped that work, and we were doing on RFI, EMC, EMI aspects of RFID design. I have a couple of papers produced in RFID design, and now we are doing on EMI, EMC aspects of RFID. For example, the RFID tag, if you put on the windshield, it will work. We are designing for RFID tag which will work on metallic surfaces. A lot of applications is coming. Like that, what is the other, what are the effects due to EMI, other things that we are working with. This is I have done in 2006 to 2008 in the University of Kent. Someone maybe is...
And Dr. Anu Muhammad has asked for a clarification regarding the transition zone which you mentioned in the opening slide, whether they are different from the antenna radiation concept that lambda
antenna radiation concept with respect to dimension of the antenna 2D squared by lambda that we are putting like that. It is nothing like it basically we are looking at the wave front. What is the Fraunhofer and Fresnel? This basically comes from the physics. The Fraunhofer and the BSc physics students, they may be knowing Fraunhofer and Fresnel region. And that type of things. Actually, there is nothing like a region you can cut like a cake and you can say that this is a far field and this is there is nothing like that. The antenna people are doing like that.
I think the query is related to the length of the probe, whether the near field, reactive near field and radiative near field are related to the anything in connection with that length of that coaxial probe.
Yeah, practical experience really required in EMC. Thanks for your presentation. I didn't see anything. Any query?
That was from Dr. Anu Muhammad. It came directly to my box. Yeah.
Okay. Yeah, I think we are all working the near field probes. We are working with the near field only. Near field, active, reactive near field only. So it will become more complex as we go to higher and higher frequencies. Yeah, it will become very complex. It will be going there because regarding EMC, other things. I am many people. You may be much better than me because EMC, EMI. Maybe many people may be much better than EMC, EMI because many of the talks I have seen, my wonderful, excellent talks. Actually, what I have to say that this is a wonderful field. If you have some pain to study electromagnetics, not by theory or mathematical derivation, in physical point of view, we study electromagnetic theory and experience. Then you can become a good EMC engineer, and there are a lot of opportunities in India. And at the time, 2008, I came. Some people, many, there were some EMC labs coming up with. They were contacted me, but basically, an academic people, we cannot go. A lot of teaching works and other things are there, so it is very difficult. Actually, by the time there was, I think Wipro has started some lab. He has a lot of work. Is now it is India. It is going on well. I think very good in EMC. At that time when I came, it was in a very, very infant stage. I think IIT Kharagpur, only many people are doing good work and even testing also. This is from my knowledge. So I am not at all working with EMC now, just like what I told, it's like EMC of RFID or that type of problems, wireless sensors and other things. I think no queries. Thank you all of you for for the nice, wonderful and hearing and the encouragements given in the chat box. Thank you all. Over to you, ma'am.
Thank you, sir. I would like to say that you have started from the basics of radiation and the fields around the radiator and the complexity in the design or modeling of all these probes, and the importance of calibration was also touched upon. And I hope all the students of the electronics department of QSAT, by now you would approach, I would suppose, the new measurement setup there with due reverence and thankfulness because of the quality and the time and the money involved in setting up such a measurement setup. And it is a very delusive phenomenon that EMI and EMC is all about. Thank you once again, Thomas Pisa, for the great presentation. And,
thank you
thanks
all.
To all the participants. And over to you, Dipti.
Thank you, ma'am. Thank you, sir. It was really good, as madam said, from the basics, all the details. I'm sure the students have benefited a lot from what you have said. Please share the slides with, if possible. Share the slides which I could share with the participants. And I request all the participants to switch on the video for a moment so that Nihal, student organizer, would take a photo.
Yeah, I got the photos.
Thank you, Nihal. So thank you, Binupal ma'am, for being here, sharing the session, making it interesting, and thank you, Thomas sir. Have more such activities in the department once the pandemic is over. Physical activity, I think, more on EMI, EMC, because I feel a lot of work can be done. Students can benefit a lot from the facility that we have at the moment. And we need to understand the basics properly. That is very important, and sir has stressed on that, and it's wonderful to have you here, sir. Thank you, ma'am. Thank you all. We'll meet tomorrow, the last day of the program. Please join on time at 4 o'clock. Thank you.
Thank you.